We're completely surrounded by waves all the time. From the music you're listening to the light coming from your screen, they are literally the invisible architects of our world. But what are they, really? Well, in this explainer, we're going to decode the secret language of waves.
So let's start with a puzzle. What on earth could a vibrating guitar string possibly have in common with a radio wave zipping across a city? I mean, they seem like they're from different planets. But the answer, it lies in the fundamental physics that governs both of them.
All right, so here's our game plan. First up, we'll nail down what a wave actually is. Then we're going to dissect one, look at its anatomy. After that, things get dramatic as we explore what happens when waves collide. And to finish it all off, we'll get to see the absolutely beautiful, stable patterns they create through something called resonance.
Okay, let's get right into it. Part 1, what is a wave? The short answer, it's all about energy on the move.
So, what is a wave, really? It's a disturbance that moves energy from one spot to another, but, and this is the key part, without actually moving any matter. The stuff the wave is traveling through, whether it's water or air or a string, its particles just kind of wiggle in place. You know the perfect way to picture this? A stadium wave. The people just stand up and sit down, but that wave of energy, that shape, travels all the way around the stadium. Now, waves basically come in two main flavors. Over on the left, you've got your transverse wave. This is where the wiggle is perpendicular, at a right angle, to the direction the energy is headed. A guitar string is the classic example. It moves up and down, but the wave travels sideways along the string. And on the right, that's a longitudinal wave. Here, the wiggle is parallel to the energy flow. Sound works just like this, by bunching up and stretching out the air in the exact same direction the sound is traveling. Okay, so we know what they are, but how do we actually describe them? Let's move on to section 2, the anatomy of a wave. We are about to decode the mathematical blueprint, the secret recipe, that describes every single wave you could ever imagine. Whoa, okay, don't let this equation freak you out. Seriously, think of it as the universal language for any wave. It might look a little intense, but it's actually this incredibly elegant way to find the exact height, y, of any part of a wave, at any location x, at any moment in time t. It's like a wave's personal GPS. So let's break down what each piece of this code really means. All right, let's decode this thing. That ym out front, that's just the amplitude. It's how tall the wave gets, its maximum height. Easy enough. K is the angular wave number, which is just a fancy way of talking about the wavelength. You know, how wide or stretched out one wave cycle is. Then you've got omega, or omega. That's the angular frequency, and it tells us how fast the wave is wiggling up and down. And finally, that whole chunk in the parentheses, that's the phase. It's like the wave's internal clock and compass, telling you exactly where you are in the cycle at any given point. So how fast is the wave actually moving? Well, that's the wave speed, which we call v. And what's interesting is that the speed isn't set by how tall the wave is, but by the stuff it's moving through, like how tight a guitar string is or how dense it is. And it all boils down to a really simple formula. The speed is just the wavelength times the frequency. That's it. So a wider wave or a faster wiggling wave is going to travel faster. Okay, section 3, when waves collide. Now this is where things get really cool. What happens when two different waves try to be in the same place at the same time? Do they crash, bounce off each other? The answer is called the principle of superposition. The source material actually says it perfectly. When two waves overlap, you just see the results of them adding together. The original waves aren't destroyed or anything. They actually pass right through each other like ghosts. But for that one instant they're in the same spot, we only see their combined effect. And this simple addition leads to two pretty wild outcomes. On the left, we've got fully constructive interference. This is when two waves are perfectly in sync. Their peaks line up with peaks, their valleys with valleys. They basically team up, and their heights add together to create a new wave that's twice as tall. But on the right, you get the total opposite, fully destructive interference. This is when they're perfectly out of sync. The peak of one wave lines up with the valley of the other, and when that happens, they completely cancel each other out. You're left with nothing, a flat line. Poof. And all of that amazing dance of interference, brings us to our grand finale. Section 4, standing waves and resonance. This is where that interference stops being just a momentary thing and starts creating these stable, absolutely gorgeous patterns. It's like a symphony of interference. So what in the world is a standing wave? Well, it's this really special pattern you get when two identical waves traveling in opposite directions
interfere with each other. And look at it, it's bizarre. The wave pattern itself doesn't actually go anywhere. It doesn't travel left or right. It just oscillates in place. It has these spots that are perfectly still, called nodes, and these other spots of maximum motion, called antinodes.
But here's the magic. You can't just create these stable patterns at any old frequency. No, you have to hit the sweet spot. At very specific frequencies, which we call resonant frequencies, the interference builds on itself in just the right way, and something amazing happens. Take a look. This is what we call the second harmonic. It's the second resonant frequency for this string. See how it's vibrating in two clear sections? And right there, in the dead center, is a point that isn't moving at all. That's a node, a spot of perfect destructive interference. Now, what happens if we crank up the frequency to the next sweet spot? We get this, the third harmonic. Now the string is vibrating in three separate sections. You can clearly see two perfectly still nodes between the ends. The pattern is getting more complex, but it's just as stable as the last one. And here we go again. This is the fourth harmonic, now with four vibrating sections. Each one of these patterns is a unique, stable mode for the string. And here's the big takeaway. Each one happens at a very specific, predictable frequency. This right here is the fundamental physics that allows a guitar string to produce clear, distinct musical notes. And resonance isn't just for one-dimensional things like strings. Look what happens on a two-dimensional surface, like a kettle drum head. When it vibrates at one of its resonant frequencies, it creates these mind-blowing, beautiful patterns. The powder that was sprinkled on there, it's all collected along the nodes, the lines and curves that aren't moving at all, making the invisible physics of the standing wave totally visible. It's incredible.
Which kind of brings us to our final thought. We've seen how waves are all about moving energy and how their interference can create these stable, resonant patterns that are the very basis of music. So it makes you wonder, where else are these hidden resonances shaping our world? From the energy levels inside an atom all the way up to the structural integrity of a bridge, the secret language of waves is absolutely everywhere.